Now the fifth problem is prove 1 plus 3 over 1 in the bracket into 1 plus 5 over 4 in the next bracket up to product of 1 plus 2n plus 1 over n square is equal to n plus 1 whole square for all n belong to n. Now the solution is that we have a result and we have to prove it, and here we have to equate this. So we have to find the solution of this. So let P of n is 1 plus 3 over 1 into 1 plus 5 over 4 up to 1 plus 2n plus 1 over n square is equal to n plus 1 whole square. That is our statement, that is called P of n. So the first step is, that is step 1. So for n is equal to 1, we have to check P of 1 is true or false. So we will take left hand side. We will replace n is equal to 1 in the last element at the left hand side. Then we get 1 plus 2 into 1 plus 1 over 1 square, replacing n by 1. Here we get 1 plus 3 over 1, that is 1 plus 3, it gives 4. So by substituting n is equal to 1 in left hand side, we get n, that is 4. And in right hand side, we get 1 plus 1 whole square is equal to 2 square is equal to 4. So from above it is clear that left hand side is equal to right hand side. Therefore, result is true for n is equal to 1. Therefore, P1 is true. Now we will proceed further after proving P1 is true. That is step 2. Now we are familiar with the step 2. We assume that result is true for n is equal to k. So we will replace n is equal to k in the left hand side and right hand side. So it becomes P of k. So P of k is 1 plus 3 over 1 into 1 plus 5 over 4 plus into so on, that is the product 1 plus 2k plus 1 over k square is equal to k plus 1 whole square. That is Pk is true. That is statement is true for n is equal to k. Now the step 3 is here we have to prove the result for n is equal to k plus 1. That is P of k plus 1 is 1 plus 3 over 1 into 1 plus 5 over 4 up to 1 plus 2k plus 1 over k square into 1 plus 2 times k plus 1 plus 1 over k plus 1 whole square plus 1 plus, sorry, not here plus, it is the product, 1 plus 2 times k plus 1 plus 1 over k plus 1 whole square. That is replacing n by k plus 1 in the left hand side in the last element is equal to k plus 1 plus 1 whole square. That is, we have to prove k plus 2 whole square in the right hand side. So here we will take left hand side. Do it carefully because a little mistake will turn the question end and you will get 0 marks in the exam. So left hand side is 1 plus 3 over 1 into 1 plus 5 over 4 into 1 plus 2k plus 1 over k square into 1 plus 2 times k plus 1 plus 1 over k plus 1 whole square. So as in the earlier problems we have done, we will take first k step, that is k element. So we will replace this result by k plus 1 whole square by using step 2. And here we get 1 plus 2k plus 2 plus 1 over k plus 1 whole square. As here we use second step result, so we write here from step 2. We have to write the reason from where we get this. So here we get k plus 1 whole square. By taking LCM, we get k plus 1 whole square plus 2k plus 3 over k plus 1 whole square. So we get here a square, k plus 1 square will be cancelled out by this and we will remain with a square plus b square plus 2ab plus 2k plus 3. That is k square plus 4k plus 4. That is equal to a square plus b square plus 2ab. So it is k plus 2 whole square, which is equal to right hand side. Therefore, pk plus 1 is true. That is, statement is true for n is equal to k plus 1. So, by principle of mathematical induction, result is true for all n. That is, Pn is true for all n belongs to n. So this was all about the problem number 5. Now the problem 6 is prove a plus a into r plus ar square plus so on ar n minus 1 is equal to a r raised to power n minus 1 over r minus 1, for r is not equal to 1 and belong to n. So here we have to apply principle of mathematical induction. Solution is that let P of n is a plus ar plus ar square up to ar n minus 1 is equal to a times r n minus 1 over r minus 1. So step 1, for n is equal to 1, p of 1 is 2 or 4. So by taking left hand side, replacing n is equal to 1 in the last element, we get ar 1 minus 1, ar raised to power 0. And we know that anything raised to power 0 is 1. So it becomes a into 1 is equal to a. And in the right hand side, replace n by 1. So a into r minus 1 over r minus 1 is equal to a. So we can say that left hand side is equal to right hand side. Therefore, P1 is true. That is, result is true for n is equal to 1. Now the step 2 is we assume that result is true for n is equal to k. That is, P of k that becomes a plus a into r plus so on a of r k minus 1 is equal to a into r raised to power k minus 1 over r minus 1. That is, P of k is true. That is, result is true for n is equal to. Now we will prove the result for n is equal to k plus 1. That will be done in the step 3. Then step 3 is now we have to prove the result for n is equal to k plus 1. That is, P of k plus 1 means a plus a into r up to a into r raised to power k minus 1 plus ar r raised to power k plus 1 minus 1 is equal to a into r raised to power k plus 1 minus 1 over r minus 1. This is our GP series up to k plus 1 term. So proving this result, we will take left hand side. That is a plus a into r plus so on a into r raised to power k minus 1 plus a into r raised to power k plus 1 minus 1. So from this we can see that up to k terms, we will replace the result by using step 2. From there we get a into r raised to power k minus 1 over r minus 1 plus a into r raised to power k. So we will take LCM and here we will write from step 2. It is necessary to write here the reason from where we get this result. So we will take the LCM r minus 1 and open the bracket. A into r raised to power k minus a plus a into r raised to power k into r minus 1. And we will get a into r raised to power k minus a plus a into r raised to power k plus 1 minus a into r raised to power k over r minus 1. That is, we get, this will be cancelled out, they are of opposite signs, and we get a as common, r raised to power k plus 1 minus 1 as a is common over r minus 1. If we see, this is equal to right hand side. Therefore, we can say that result is true for n is equal to k plus 1. That is, p of k plus 1 is true. Therefore, by principle of mathematical induction, Pn is true for all n belong to n. So this was all about the problem number 6.